Hello everyone, and thanks for watching Edupedia World Videos. This is the third video in the chapter Current and Electricity, and in this video we'll be learning about the functioning and working of batteries. We've used batteries in circuits before, but we haven't really understood how they work internally, and so this is what we know about batteries so far. If we have a battery which has a potential difference of V across its ends, we can take this to be potential 0, and we can take this end to be potential V, and if this end has a resistance R, then current will flow from the positive end of the battery to the negative end, and the current I will be equal to V by R, because by applying Ohm's law across this resistor, the potential difference across this resistor V, because this is V and 0, will be equal to the current across this resistor multiplied by the resistance. Now, right now we'll try to learn how a battery can create a potential difference of a given potential difference. So there are many different variations of batteries, and you'll learn a little bit about them in your chemistry classes. We'll not discuss that in detail right now. Right now we'll just assume that within a battery you have a force which is non-electrostatic in nature. It could be due to the forces applying by the rods on the solutions. In the case of a chemical battery, I'm sure you studied some of those in your previous classes, but the mechanism here doesn't matter. Here all that matters is this is the battery which has some chemical substances in it, and in the battery from one end to another there is a force Fb. Now this force is non-electrostatic in nature, and this is the force due to the battery. That's why we call it Fb. Now the direction doesn't matter. I've just chosen one direction arbitrarily, but the force Fb is such that if the direction of the force is towards left, then the force on positive charges will be towards left, and the force on negative charges will be towards right. And right now we're assuming that this battery is not connected to anything. So what will happen is, because of this Fb, positive charges will flow to the left and negative charges will flow to the right. That means we'll have an accumulation of some positive charges on this end and some negative charges on this end. Now what will happen is very similar to what happens when we place a conductor in an electric field. These charges will create an electric field towards the right. The positive charge will create an electric field away from it towards the right. The negative charge will create an electric field towards it, towards the right. Now initially, let's call this Fe the electrostatic force. Now again, this difference needs to be clear initially because this will come up again and again. Fb is the force due to the battery, and it could be due to a variety of things. Fe is the electrostatic force, and it is created by the accumulation of these charges. The charges themselves are accumulated due to Fb. Right, so initially Fe will be small, and there will still be a net force towards the left on the charges, on positive charges. So we'll have a greater accumulation of charge that will increase the magnitude of Fe until finally in steady states we will have the magnitude Fb is equal to Fe. And in that case we will have a constant positive charge density on the left plate and the negative charge density on the right plate, and there will be no more charge accumulation because the net force on any charge will be 0, because Fb and Fe are equal and opposite. Now if I were to take a single charge Q from the negative terminal to the positive terminal, what will be the work done by the battery? Let's say this distance is d, then the force on this charge Q due to the battery will be Fb, right? And the work done by this battery will be Fb times d, because we are taking the positive charge from the right side to the left side. So this is the direction of displacement, and this is also the direction of Fb. So Fbd will actually be the work done on this charge Q by the battery. What is Fbd by Q? It is the work done by battery per unit charge. And this quantity is labeled as E and is called the EMF of the battery. So the EMF of the battery, it's a specific value for every battery, and it is basically the work done by the battery in transferring a unit charge from the negative end to the positive end. Now, the important thing to remember is that this is the work done by the battery, not the work done by the electrostatic forces. Right. Also, another thing, the full form of EMF is electromotive force. And this is one of those situations in physics where the naming is slightly unfortunate, because this misleads people into thinking that EMF is a force. EMF is not a force, it is the work done by the battery per unit charge. To be honest, I really don't understand why historically it started being called electromotive force and why it took up. But that's what I learned when I was studying physics, so that's what I'm telling you. E is called EMF or electromotive force, even though it is actually the work done by the battery per unit charge. Right. Now this is something that will always happen, but let's look at what will happen in steady state, that is when FB is equal to FE. In that case, we can write E as FE d by Q. Right. Now FE can be written as Q times the electric field in this direction. Remember, FB has no corresponding electric field because it is the non-electrostatic force due to the battery. FE is the electrostatic force created by this positive and negative charge, so it will have an electric field to accompany it, and FE will be equal to Q times E. Right, FE is the force on a charge Q into D by Q, which gives me E into D. And what is E into D? It is V. It is the potential difference between these two terminals. So from this we get an interesting result. E is equal to V. And this is a point which is a source of confusion for some students. E and V are completely different things. V is the potential difference due to the electric field created by the positive and negative charges. It is something which we've seen again and again and again. But E is something which is new. E is the work done per unit charge by the force of the battery in taking a unit charge from this point to this point. Now this basically states that E is equal to V in cases of steady state. That is when FB is equal to FE. Initially, when you start a battery, there is no reason FB will be equal to FE. In fact, FB will be dominant and it will create an accumulation of charges. Once enough charges have been accumulated that FB becomes equal to FE, there is no more accumulation of charges, the charge densities remain constant, and we have what is called a steady state. It is also said that E is equal to V. That is, E is the potential difference between the ends of the battery when the battery is not connected externally. But that's just one way of saying that when the battery is not connected externally, eventually it will reach steady state. Right? Because if you just leave a battery like this, there is no other option other than for it to reach steady state. Now let's try to apply batteries as they work in circuits. So what we'll do is we'll take this same battery and we'll just apply it to a circuit. So let's say this is the positive end, this is the negative end, this is the direction of FB, this is the direction of FE. This will basically generally be represented in circuits as this. The positive end will have a bigger line, the negative end will have a smaller line. Right. So let's say we connected this to a circuit, and for now we'll not take any resistors, we'll just take a standard conducting wire. So now we'll focus on this conducting wire. In this conducting wire, let's say this has a potential of 0 and this has a potential of V. This side has a higher potential than this side. So what will happen is an electric field will be created in the conductor in this direction. And if an electric field will be created in the conductor in this direction, that means positive charges will flow from this end and go all the way around and come back through this end. Now actually we discussed this in a previous video, that's not technically true. What will actually happen is the electrons will move from the negative end to the positive end. Right, because electrons are the mobile charge carriers, or protons are generally more stationary. They have lower mobility. So, but whenever we say current is flowing from this end to this end, what we really mean is electrons are flowing in the opposite direction. So from now on that should be understood. Whenever I say positive charges flow from this point to this point, that really means that electrons flow from this point to this point. Right. So what happens when a small charge goes from this point to this point? This positive charge decreases and this negative charge, the magnitude decreases as well, because you might have a certain charge adding into it. So if this is -5, it will become -4, let's say. So both these charges magnitude decrease, that means the electric field decreases. So if the electric field decreases, FB becomes more than FE, it becomes more dominant, and because of the difference between them, charges are taken from this end to this end, which reinforces the original surface charge density. So the surface charge density tends to decrease because of the current flowing through the wire, but it tends to increase because of the current flowing into the battery. And this is the mechanism by which a battery maintains a constant potential difference and ends up creating a constant circuit flowing in a wire. Constant current flowing in a wire. Now let's look at what happens when we have a resistance within the wire. So from now on, I'm just going to draw the batteries like this. And up till now, we haven't really seen the difference between E and V. We'll see that in a few minutes when we see that batteries can sometimes have their own resistances. Right now, we are not considering that. Yeah, so let's say this is 0, this is V, or E, which is the EMF, whichever you want to take it. The resistance is R. Current flows in this direction, equal to I. We know that V is equal to IR. What we would like to find out is the energy that is dissipated within this resistor. That means there is work done by the battery in taking charges from this end to this end, and that work done is ultimately manifested as energy lost by the resistor, which ends up in heating of the resistor. So we need to find out what that work done is. So in time t, an amount of charge IT will flow from this end to this end, or from this end to this end, like this, right? So this is the amount of charge flowing. If this amount of charge flows from this end to this end, which have a potential difference V, then what is the work done? The work done will be IT times V. Now we know V is equal to IR. From that, what I get is the total energy that is dissipated within the resistor is equal to IR times IT, or I square RT. From that we get the power, which is the energy dissipated per unit time, is I squared R, or sometimes it is referred to as V squared by R. Doesn't matter, right? So this is the power dissipated by the resistor, and it is ultimately lost as heat, and the resistor tends to become hot. Now what we've discussed up till now is the working of an ideal battery, and in an ideal battery what happens is, let's say a charge Q, which might be equal to IT, flows from this end to this end within the battery and along this direction within the circuit. In that case, the work done by the battery, by the force due to the battery, will be it will be the EMF multiplied by Q. The EMF is the work done in taking 1 unit charge from this point to this point, so EQ will be the total work done by the battery. What will be the work done by the electrostatic forces, that is the positive and negative charge densities taking the charges through the wire? That will be V times Q, right? Now in most cases EQ will be equal to VQ, that is E is equal to V, and everything will be fine. However, in some cases EQ and VQ will not be the same, and there will be some amount of energy difference that will be lost as heat. And how is energy lost as heat in circuits? It is lost through resistors. So in cases where E will not be equal to V, remember E will always be equal to V if nothing is connected. If a circuit is connected, then E may or may not be equal to V. And experimentally, if we find out that E is not equal to V, that means there is some energy lost, then there is only one solution. The battery has to have its own internal resistance. That's why I said in the beginning, E is the EMF, that is the potential difference across the terminals of a battery when it is not connected to anything. If it is connected to a circuit and it is an ideal battery, even then E will be equal to E. But sometimes a battery might have its own resistance. In that case, E is not equal to V. So let's see what happens in that case. This will be how the battery is represented. The EMF is E, the resistance is R. Now, sometimes students get confused in this, but actually there's a very simple concept you need to remember. Earlier we were talking about this as the battery. Now we are talking about this whole thing as the battery. Right. Except EMF will still be the potential difference across these two ends, because EMF is the work done in taking a charge from this end to this end. So now if this is at a potential 0, then this will be at a potential E. Right, and let's say it's connected to some circuit, charges will be flowing in this direction. In that case, because there is a resistance and charges are flowing in this direction, this point has to be at a higher potential from this point. If the current is I, then the potential difference across these two terminals will be IR, and this will be at a lower potential, so the potential here will be IR. So in that case, the EMF of the battery is still E. But what is the potential difference across these two ends, which is technically the potential difference across the ends of the battery? That will be E minus IR. See, so E has a very specific meaning, EMF. It is the work done in taking a unit positive charge from this end to this end. V has a very separate meaning. It is the potential difference between the two ends of the battery. In special cases, they might be the same. For example, when the battery is not connected to anything, or if the battery is not connected to anything, even in this case like this, then I will be 0 because there is no current flowing from one point to another. So these will be at the same potential. So whenever a battery is not connected to anything, the EMF is equal to the potential difference between the ends. That is also true when the battery is connected to things, but it does not have an internal resistance. However, when a battery has an internal resistance and is connected to a circuit, the EMF, that is the work done in taking a charge from this end to this point, is not the same as the potential difference between the two ends, and we need to take care of that. Now we've seen the concepts on series and parallel for resistances, capacitors, and even rods when we were doing heat transfer, but the same concept can be applied to batteries. So now we'll try to find out the equivalent EMF and the equivalent internal resistance for a group of batteries placed in series or parallel. Let's do series first. Right, so this battery has an EMF E1 and a resistance R1. This has an EMF E2 and a resistance R2, and we connected this whole system. This is now our system of batteries, and we've connected it externally to a resistance R. Now this R might be a simple resistance, it might be a capacitor, it might be a whole combination of things. Right now we're just taking the simple case because we'll find out the equivalent EMF and resistance. Then we can just apply the concept to the whole circuit, no matter how complicated this is. Because ultimately, these ends are the only thing we are concerned with. So what is the meaning of the equivalent resistance and EMF? Remember, the characteristic of a battery in a circuit is how much charge or how much current it produces. So we would like a particular battery of EMF E0 and an internal resistance R0, such that if instead of this system we were to place a single battery of EMF E0 and internal resistance R0, it would ultimately give us the same current flowing through this resistor. That's what we are looking for. So in this case it's quite easy. We'll just use Kirchhoff's voltage law across this loop, and we can start from any end. Let's say we start from this end. In that case, going through this direction, we'll have a potential drop of IR, so it will be minus IR, right? Potential will drop. Then we go here, current is going from this point to this point, so the potential will drop again, so minus IR1. Then the potential will rise by E2. Then the potential will drop again, minus IR2, because this point is at a higher potential than this point, because current flows from higher potential to lower potential. Plus, then this will be again E1, and that has to be 0. That has to be the potential of this point again. So what that gives me is I into R plus R1 plus R2 is equal to E1 plus E2, or what that gives me is I is equal to E1 plus E2 by R plus R1 plus R2. We can write this as E0 by R plus R0 if E0 is equal to E1 plus E2 and R0 is equal to R1 plus R2. Now keep in mind, if we just had a single battery of EMF E0 and resistance R0, then the equation would be minus IR minus IR0 plus E is equal to 0, or the current will be E0 by R plus R0. And since E0 is equal to E1 plus E2 and R0 is equal to R1 plus R2, these are the equivalent EMFs and resistance for batteries in series. Now you could have 2 batteries or you could have 20 batteries. All you need to do is add the individual EMFs, and that will give you the net EMF across the two ends, and add the individual resistances, it will give you the net internal resistance. Now this is just a construction. All that it says is, instead of this whole system, I could have just scratched this out and instead just kept one single battery of EMF E0 and internal resistance R0, and nothing in this external circuit would have changed, right? So this is for series connection. Just to remind you what happens in series the current remains the same across the batteries, the potential difference adds up. Now let's look at what happens when we have two non-ideal batteries, that is batteries which have an internal resistance, and we add them in parallel. So let's take a circuit like this. Yeah, so this is E1, R1, E2, R2, capital R. Right. So this it should be in this direction because both these terminals are positive. So current will flow in this direction. Now all we are looking for is a particular E0 and a particular R0 such that if E0 was the EMF of the battery, R0 was the internal resistance of the battery, then the current flowing through this would be the same. If we had just a single battery of E0 and R0, then we know the current would be E0 by R0 plus capital R. So we need to find out the current right now, and we need to write it in this form, and from that we will be able to extrapolate E0 and R0. So we can do this in many ways. I'll just try one method. Let's say this total current is I, so this is I1 and this will be I minus I1. So we can apply our KVL rule across this loop, across this big loop, or across this loop. I'll choose two loops, both of them including R, because I've done this before and I know mathematically that will be simpler, but I suggest you try it in all possible combinations. So the first, if you start from here, the first law will be minus IR, then going in this direction, minus I minus I1 R2 plus E2 is equal to 0. Then for the upper loop, we'll have minus IR minus I1 R1 plus E1 is equal to 0. Now the first step I'll try to do is I'll try to eliminate our I1 because I1 is something we don't know, right? So first I'll try to simplify this a little bit. These are the two equations. So the first equation can be written as minus I times R plus R2 plus I1 R2 plus E2 is equal to 0. And the second equation is written as minus IR minus I1 or minus IR plus R1 plus E1 is equal to 0. Right. I made a mistake. This should be just I1, yeah. So the second equation will be minus IR minus I1 R1 plus E1 is equal to 0. Now from these two equations we need to eliminate I1 because that's something we don't need, that's arbitrary. So the best possible way you can see it right now, I'm sure, we'll multiply this by R1 and this by R2 and add them up. Right, so this will be I1 R1 R2 and this will be minus I1 R1 R2, so both of them will cancel. So I'll just write it straight away here. So we'll multiply this whole equation by R2, right? So we'll get minus I R R2 plus E1 R2 plus, now we'll add this one, multiply this by R1, right? So we'll get minus I R R1 minus I R2 R1 plus E2 R1, and this whole thing is equal to 0. From this, if you calculate the current, it will come out to be, I'm running out of space, so I'll just rub this main circuit. I hope you don't mind that. Yeah. So what I'll get is I is equal to E1 R2 plus E2 R1 by R R2 plus R R1 plus R2 R1. Now from right now the physics of the question is over. Now we just need to apply a little bit of mathematics, and I just tell you how it's done because to explain how it's done I don't even understand exactly how I would explain it to you. This next step comes from mathematical intuition, but we need to write this as something like this. So what we'll do is we'll divide both these sides by R1 plus R2, and we can see that I is equal to E1 R2 plus E2 R1 by R1 plus R2 by, I mean, if you just write it as this and you try to equate it, even then you'll get the answers, divided by, now we'll divide this by R1 plus R2 as well. So the first term is basically R times R1 plus R2, right? So if we divide by R1 plus R2, this will cancel. So we'll simply get R plus R1 R2 by R1 plus R2. And we needed it in this form and we have it in this form. So you guess the answer. The equivalent EMF is equal to E1 R2 plus E2 R1 by R1 plus R2, and the equivalent internal resistance is equal to R1 R2 by R1 plus R2. If you notice, the internal resistance is the same if we just had two internal resistances in parallel, right? So this completes batteries. In the next chapter, we'll see how we can use different instruments to measure particular things in circuits such as ammeters and voltmeters. Thank you.